Hello everyone, this is a project on Cranial Remolding Helmet, which is done by myself, Bryce, Zackary and Etienne, and this project focuses on infants with cranial deformations, which will be talked about in the next slide.
Cranial deformations are defined as abnormalities of the original skull geometry. In infants, these abnormalities occur primarily through the development of flat spots. These flat spots can occur before birth, also known as craniosynostosis, or after birth. Cranial deformations can vary and are classified depending on the location of the flat spot. Approximately 45% of infants are impacted by these cranial deformations. Currently, the only solution that is marketed to treat these flat spots are cranial remolding helmets, as pictured on the right. These devices are currently not covered by healthcare insurance since cranial deformations are classified as a cosmetic concern. These devices can cost anywhere between $1,300 to $3,000 depending on the modifications required as the infant continues to grow. These helmets are outgrown, requiring additional custom helmets to be created as the infant ages. Our motivation for this project was to design and develop a novel infant helmet which would correct these cranial deformations and allow for the infant's head to grow into the ideal geometry. The novel design would be an improvement of conventional infant helmets in that it would be more biocompatible with the infant's skin, preventing any irritations from developing. The device would also have a more breathable design, allowing more airflow to the infant's head, and would be lighter, enabling the infant to move their head easier. Also, since these devices are not covered by healthcare insurance, this device would be more affordable for families. In order to scale the 3D model of the device properly, scans of an anthropometric infant mannequin were taken using a mobile application called Polycam. Using Polycam, 3D scans of the mannequin head were taken and exported to SolidWorks as an STL file. Originally, the model of the head was too rough and jagged and was not representative of the mannequin's head. To correct this issue, the STL file was uploaded to MeshMixer, where it was then smoothed and edited. After smoothing the model in MeshMixer, the file was then uploaded back into SolidWorks for modeling with the 3D helmet.
The untraditional design is centered around three principles: customizability, biocompatibility, and affordability. The helmet is custom made according to the infant's exact measurements that are taken physically and virtually from the 3D scan. The natural curve of the infant's skull is used to formulate the basis of the design, and a fit test is conducted through a SolidWorks assembly, and this is shown in a later slide. There are 2 1/4-inch thick layers consisting of an interior layer made of thermoplastic polyurethane, or TPU, featuring a honeycomb pattern for breathability, as well as an exterior layer made of polylactic acid, or PLA, modeled after a cycling helmet for its rigidity and airflow. TPU is known to be an excellent flexible biocompatible material that can conform to the infant's head while providing a cushioning layer for safety. Affordability was a main design component due to the exorbitant cost of professionally manufactured headgear. The model consists of a TPU 3D printed part, a PLA 3D printed part, Velcro strips, and high-density foam. Prototype 1 can be seen in the right of both images, shown consisting of a black TPU layer and a spray-painted silver TPU layer. Excessive supports were used to ensure print integrity. However, removal proved difficult, so a combination of physical and chemical methods were used. The TPU supports were removed using a heat gun and dimethyl sulfoxide, or DMSO. The PLA supports were removed using a belt sander and sodium hydroxide, commonly known as lye. Prototype 2 is constructed with the same materials and file. However, it was printed by AVC, which only put supports on the PLA layer, which was easily removed using pliers and sandpaper. Assembly of the device was done using a combination of glue and Velcro. Hot glue was used to secure the Velcro strips and foam to the helmet. The Velcro strips have adhesive backing, but hot glue was added additionally for improved adhesion. Velcro strips were secured on the top of the interior layer and underneath the exterior layer, enabling the helmet to be easily disassembled. As shown in the left image, the parts were placed in an assembly in SolidWorks to show how they fit on the head. The middle image shows Prototype 1 with its static Velcro strap and radial foam placement secured on the mannequin. The image on the right shows Prototype 2 with its dynamic Velcro strap and posteriorly focused foam placement on the mannequin head. Alright, here is a demonstration of the first working prototype that we did. All it is to assemble it is these Velcro strips line up with this back. and then it gets placed on the baby using the strap.
Here is the demonstration of the second working prototype. It is the same method with the Velcro strips on the inside, and you would just stick it in right here, and we do have an adjustable Velcro strap, which will then be modeled on the mannequin.
Hello everyone, this is the working CPR doll that we will be using to test both prototypes on, more importantly the second prototype, and you will see it in a few seconds how we will fit it onto the infant's head. So this is the fitting of the helmet onto the infant. As you can see, we have adjustable straps in which we use the Velcro, and it's more aligned with the chin itself and not the neck to avoid any blockage of the breathing areas. This is the final fitting onto the doll itself. You can see an all-around view of the helmet, and just for testing purposes, if we were to tilt the baby, don't do this at home, it would be easily fitted onto the helmet.
This video is to demonstrate that while sleeping, the infant's airway is not obstructed while wearing the helmet.
So this is the force gauge that we use to measure the amount of newtons that could be applied to this helmet. From this lever, it records the amount of newtons that are displayed, and it can also record the displacement of the helmet when a force is applied, and you have your resulting force along with your resulting displacement.
For the main results as demonstrated in the video with the force gauge experiment, we conducted a stress test on all the sides of the helmet to see how much force could be applied before it deforms or starts to crack. For the top, side, front and back of the helmet, it had approximately the same maximum displacement, and it could also be seen that from the top of the helmet, as shown in the dark green on the graph itself, it can withstand the most amount of force, which ensures the protection of the infant's head. So in conclusion, infant helmet was made from 3D printing, in which the outer layer was made of PLA, which provided protection and also could withstand a high amount of force, while the inner shell was made up of TPU that was used to conform to the infant's head. This helmet provided a secure fit, as it was seen fitted onto a CPR doll in the video before, and this allowed for the growth of the infant's head while also maintaining its protection. So there were very cost-effective ways to go about this, and this helmet roughly costed around $15 to make, which can provide similar results to the helmets that already are on the market. Of course, there are always ways that we can improve upon this, which will be explained in the next slide. So for future works on the design of this project, one of the main improvements that we can use is a softer PLA material or more flexible PLA material instead of the TPU layer, since the TPU was found to be more rigid than we expected and resisted a lot of deformation when we tried to tighten the straps to the baby's face. The softer PLA can also conform easier to the baby's head, while also providing a softer layer which can promote less skin irritation. In efforts to better secure the helmet to the baby's head as well, we can also try to upgrade the current adjustable strap to more of a tightening mechanism, as seen in the middle figure, which could also use to avoid the need for a chin type strap that can 1. Annoy the infant, 2. Cause skin irritation, or 3. Reduce the chance of blocking the infant's airways. Another future improvement that could be implemented is to add extra support to the infant's neck within the helmet itself, so that it could promote proper spine development at young ages. Lastly, a sleeker design could be implemented so that the helmet can conform to the baby's head more easily. In addition to this, the use of multi-directional impact protection system, or MIPS for short, can also be implemented, which is used as a slip plane design to manage energy from rotational and angular impacts, which is commonly used in bicycle and construction helmets. This design started the idea of initially using 2 layers, so that the slip layer, or the MIPS for short, could be later incorporated into the successive prototype that we further implement. So this layer will help protect the baby's deformed head from further injuries due to that slip plane via any falling or head traumas, while preserving the formation of the deformed cranium.